Okay, in today's lecture, we're going to finish the section 1.5 material on solution sets of linear systems. And in this section, we're going to talk about two different types of linear systems, namely homogeneous or non-homogeneous linear systems, and see a relationship between the solution sets for those types of systems that have the same coefficient matrix. So let's start by defining what we mean by a homogeneous linear system. So we would say that a system of linear equations is said to be homogeneous if it can be written in the form of a matrix equation of the form A times X equals to 0, where A is some m by n coefficient matrix and 0 is the zero vector. That is the vector of all zeros. So any linear system where each of our linear equations is set equal to 0 is called a homogeneous linear system. Now for homogeneous linear systems of the form AX equals to 0, we always have at least one solution. Now one solution that we always have for a homogeneous system is the zero vector itself. If we take X to be the vector of all zeros, then the matrix A times X, well, since X is the zero vector, would return a vector of all zeros. So since this solution will always work for a homogeneous system, it is sometimes called the trivial solution. That is, if we let each value of X equal to 0, well, certainly each of our equations can be made equal to 0. So what we're really interested in for the majority of homogeneous systems is whether we have a non-trivial solution. So what we mean by a non-trivial solution is some non-zero vector X, that is a vector of entries that are not all 0, such that A times X can be made equal to 0. So this question of interest can be answered by the following theorem. What are the conditions for which a non-trivial solution exists? And here they are. So any homogeneous equation of the form AX equals to 0 will have a non-trivial solution, that is something other than the zero vector, if and only if the equation has at least one free variable. So as we've seen from our earlier work, if we express a linear system or a matrix equation in terms of an augmented matrix, we'll have a free variable if within that augmented matrix we have a row of all zeros, at least one row of all zeros. So that will be our condition for testing whether a homogeneous solution would have a non-trivial solution. So let's look at some examples of this. So in our first example, we're asked whether the following homogeneous system has a non-trivial solution, and then describe our solution set. So here we have a system of three linear equations in the three variables x1, x2, and x3. And we see that each of these equations is set equal to 0. So we could say that this is a homogeneous system, since each of these equations is set equal to 0. Now just for a little review of what we've seen in earlier sections, recall that we could express this linear system as a matrix equation by writing this in the form AX is equal to B, where A is the coefficient matrix for this system. So our first row would be 1, -3, 7. Our second row is -2, 1, -4. And our third row would be 1, 2, 9, times some vector of the unknown variables, x1, x2, and x3. And this would be equal to the vector of constants on the right-hand side, 0, 0, 0. So here we do have a homogeneous system, something of the form A times a vector x is equal to the vector of all zeros, which is called the zero vector. So the question is whether we have a non-trivial solution, and the theorem that we just discussed said, well, the only way that we do have a non-trivial solution is if we have at least one free variable. So let's go about trying to solve this system by looking at its augmented matrix. So here the augmented matrix for the system is 1, -3, 7. -2, 1, -4, 1, 2, 9, and our vector b, which was the right-hand side of our equation, is the zero vector. So to solve this, we want to make use of row reduction to put this matrix in row echelon or reduced row echelon form. So starting with our first row, we have a lead coefficient of 1. And we need to get rid of the -2 and +1 that appear below that term. So to get rid of the -2 term, I could take my second row and add to it twice the first row. And in this same step, I'm going to take my third row and subtract the first row from it to eliminate the 1 as the lead coefficient in my third row. So for now, my first row remains the same. I have 1, -3, 7, 0. When I perform this operation on the second row, I have 2 minus 2 is 0. -6 plus 1 would be -5. 14 minus 4 is 10. And then 0 plus 0 is still 0. And if I perform the row operation that I've indicated on my third row, by subtracting the first row from it, I have 1 minus 1 is 0, 2 minus the -3 gives me a +5, and 9 minus 7 leaves me with 2, and then my 0 minus 0 is still equal to 0. So now I have a 1 as the pivot in that first row and zeros below it. So now moving to the leading term in my second row, I've got a -5, and I see that pretty easily I could eliminate the +5 that appears below it by adding that second row to the third. So in this step, let me start by taking row 3 and adding row 2 to that third row. So for now, my first row again remains the same, 1, -3, 7, 0. And when I add the second row to the third row, my third row will become 0, 0, 12, 0. Now, in this same step of my row reduction, I know that I would like to have this lead coefficient of my second row be a +1 to try to put this in reduced row echelon form. So if we look at each of the entries in that second row, we see they're divisible by 5 or -5. So in order to get that 1 coefficient in my second row, I could take my second row and divide through by -5, or take -1/5 of the second row. Leaving me 0, 1, -2, 0. So we're getting a little closer to reduced row echelon form. Now we don't really need to get this completely into reduced row echelon form because I could solve for x3 and then use back substitution to get my other variables. But just for a little extra practice with reduced row echelon form, let's keep moving through this system. So from here, if I wanted to keep simplifying, well, I have a 1 as the lead coefficient in my first two rows. Now I need to eliminate the -3 above the 1 in my second row. So to do that, I could take row 1 and add 3 times the second row to it, which makes my first row 1, 0, Negative 6 plus 7 gives me a positive 1, and then 0 plus 0 is 0. My second row, I'm going to leave alone for now. We have 0, 1, negative 2, 0. And in my third row, this lead coefficient is 12. Now to get this into reduced row echelon form, I'd like to have it be a 1, which we could get by multiplying my third row through by 1/12. So that gives me a 0, 0, 1, 0 there. So we're almost done. In the first two columns, we have these 1, or first two rows, we have 1 as our leading coefficients and zeros above and below those terms. And in my third row, I have a 1 as the leading term, but I need to eliminate the positive 1 and negative 2 that appear above it. So to do that, well, to get rid of the 1 in my first row, I could take row 1 minus row 3, which makes my first row 1, 0, 0, 0. To get rid of the negative 2 in the last column of my second row, I could take row 2 plus twice row 3, giving me 0, 1, 0, 0. And my last row remains the same, 0, 0, 1, 0. So what we find by looking at the equations that these rows represent, well, my first equation says that x1 has to equal 0. My second equation, or second row, says x2 has to be 0. And my third row says x3 has to be 0. Or in vector form, the vector x has to be the 0 vector. That is the vector of all zeros. So here we only have the trivial solution. There is no non-trivial solution of this system since we didn't have a free variable. Here to answer our question, we could say something like only the trivial solution namely the 0 vector, x equals to 0, exists. That is our only solution of this system. So let's look at another example. In our next example, we are asked to, again, determine whether the following homogeneous system has a non-trivial solution and describe our solution set. So again, here we have a system of 3 linear equations in 3 unknowns, x1, x2, and x3. And since each equation is set equal to 0, this is a homogeneous system. So in order to determine whether a non-trivial solution exists, well, let's look at our system and see if there is some free variable. So let us consider the augmented matrix for this system. Our first row will be 1, 1, negative 3, 0. Our second row is 2, 3, negative 2, 0. And our last row is 4, 3, negative 16, 0. So again, using row reduction to try to put this matrix in row echelon form or reduced row echelon form, let's see what we can do. So again, in our first row, our leading coefficient is 1, and we need to eliminate the 2 and 4 that appear in the second and third rows below that. So for my second row, to get rid of the 2, I could take row 2 minus twice row 1. So my first row is still 1, 1, negative 3, 0. In my second row, let's see what we have. Negative 2 plus 2 is 0. Negative 2 plus 3 is 1. Positive 6 minus 2 is 4. And 0 minus 0 is 0. Now in this same step, let's eliminate the 4 in our third row for that lead coefficient. So I could take, for instance, row 3 minus 4 times row 1. Also, I could have taken row 3 minus 2 times row 2. There's a few ways we could go about simplifying. But if we work with row 1, let's see what we have. We've got negative 4 plus 4 is 0. Negative 4 plus 3 is negative 1. We've got a positive 12 minus 16 is negative 4. And then 0 plus 0 is 0. So at this stage, we can see that our second and third rows are identical. One is just the negative of the other, but they're defining the same linear equation. So we do expect to have a free variable here. When we add those two rows, we get a row of all zeros. So immediately we suspect that there is a non-trivial solution of this system based off the theorem that we started with in this section. So let's go ahead and see if we can describe that solution set. So to keep simplifying here, we could take row 3 and add row 2 to it, which makes my third row 0, 0, 0, 0. My second row, I'm going to leave alone for now, 0, 1, 4, 0. And in the first row, I'm going to simplify a little bit. I had a 1 as the lead coefficient for my second row. I already eliminated the negative 1 below it by adding the second row to the third. And to eliminate this positive 1 above it in the first row, I could take row 1 and subtract row 2. So in the same step, taking row 1 and subtracting row 2, we have 1, 0, minus 3 minus 4 is negative 7, and 0 minus 0 is 0. So here we have our matrix in reduced row echelon form, and since we have a row of all zeros, there are infinitely many solutions which we can describe by introducing a free variable. So since my third column did not have a pivot position, I'm going to let that variable, or the variable for the third column, namely x3, be my free variable. So let's let x3, and maybe I'll make a specific choice for x3. Let's call it some real number t, be a free variable. Now, whatever value I choose for x3, I'm calling my choice t, I still need to find x1 and x2. So looking at my first row of this augmented matrix in reduced row echelon form, the first row in equation form says 1x1 minus 7 times x3, that is 7t, has to equal 0. Or equivalently, x1 is equal to 7t. And looking at the second row of this augmented matrix in simplified form, we have 1x2 plus 4 times x3, which we chose to be t, is equal to 0. Therefore, x2 is negative 4t. So to write out our answer, we would say the solution set would be the set of all vectors, if we write this in vector form, x, of the form where x1 is equal to 7t, x2 is negative 4t, and x3 is equal to t. Or if we want to rewrite this a little bit, we could rewrite this as the column vector 7, negative 4, 1, all times our choice of t, where t could be any real number. So here, our solution set, if we're trying to describe this solution set, well, it is the set of all scalar multiples of this vector, 7, negative 4, 1. We're just multiplying it by some real number t, and for different values of t, we're just scaling the length of that vector, or maybe reversing its direction. So this solution set would be describing a line in space, since this is a three-dimensional vector, which passes through the origin, since if t is 0, we have the vector 0, 0, 0, and moving along the direction specified by the indicated vector 7, negative 4, 1. So here, our solution set is a line in space, that is R3, through the origin, in the direction of this vector, 7, negative 4, 1. We're just looking at all scalar multiples of that vector, which would describe some line moving in the direction of that vector. All right, so let's look at some other ones. In this next example, we've got the same sort of question. We want to know whether the following homogeneous system has a non-trivial solution, and again, describe our solution set. So here we have a system of two linear equations in terms of three variables, x1, x2, and x3. So again, when we have a system with fewer equations than variables, that sort of system is called an underdetermined system. And we recall that typically for underdetermined systems, we'll have infinitely many solutions. Not always, but in a lot of cases. So let's look at a underdetermined system which is homogeneous. That is where we have each equation set equal to 0. So to try to find our solution set for this system, we will express this as an augmented matrix, where our first row is 1, negative 2, 6, 0. And our second row is negative 2, 4, negative 12, 0. Now pretty quickly you can see here that the second row is a scalar multiple of the first row. So if we wanted to simplify this using row reduction, well, our first row has a lead coefficient of 1, so we'll use that as a pivot to kill off the negative 2 below this. So we would have row 2 plus twice row 1, which makes my first row 1, negative 2, 6, 0. And my second row becomes 0, 0, 0, 0. So we have a row of all zeros, which means that we have infinitely many solutions here. And this matrix in reduced row echelon form only has a single pivot column, namely the first column. And there are two columns, namely column 2 and column 3, which do not have a pivot position. Therefore, each of the variables corresponding to those two columns will be a free variable. There is no restriction on what we can choose for that value. So in this example, let's choose two free variables. Maybe x2 for the second column. Let's call our choice of x2t. And x3, the variable for my third column, let's call it a different choice, maybe s, be free variables. Now, once we've made our choices for x2 and x3, we still need to find x1. So looking at the first row of this augmented matrix, in equation form, we have 1x1 minus 2 times x2, which was t, plus 6 times x3, which we chose as s, has to equal 0, or equivalently, x1 has to equal positive 2t minus 6s. So we're ready to write out our solution set. Here, the solution set would be the set of vectors x, which could be written in the form x1, x2, x3, where x1 is 2t minus 6s, x2 is t, and x3 is s, which we could split in the following way. If we were to factor this vector into two parts, one vector corresponding to the coefficients of t and one corresponding to the coefficients of s, we could rewrite it in the following way. So if we pull out a t from each term, let's look at the coefficients of t. We had a 2t, 1t, and then there was no t in our third component. So I could write this as times 2, 1, 0. And then we are adding the components of the variable s. Let me use a different color. So for s, for our first component, we had a coefficient of negative 6s. For the second component, there was no s. And for our third component, we had 1s. So we could write this as s times the vector negative 6, 0, 1, such that t and s are any real numbers that we want. So this would be our solution set, and we're asked to describe this solution set. So what we're talking about here is a linear combination of two vectors. We have vectors, let's maybe give them names, say A and B, in space. They're three-dimensional vectors, and we're looking at scalar multiples of those two vectors. We're multiplying one by t and the other by s and taking their sum. So we're looking at the set of linear combinations of those two vectors in space, or the span of those two vectors in space. Now recall from our earlier section, the span of two vectors in space would be, as long as they're not scalar multiples of each other, which we can see they're clearly not here, would be a plane which contains those two vectors. So here we have a plane in space spanned by these vectors A and B through the origin. Now, why through the origin? Well, since we can choose t and s to be anything we want, if we chose t and s to both be 0, we see that x would be the vector of all zeros, so we would have to pass through the point 0, 0, 0 in space, or the origin. All right. So we saw from the last example that if we had a single free variable, we could think about the solution set as being a line through space, or whatever dimension we're in. And if we have two free variables, then our solution set is a plane in space passing through the origin, being spanned by two vectors. So these last two examples are illustrating sort of a general way that we could write our solutions. So what we're going to describe next is what's known as the parametric vector form of a solution. Let's suppose that we find the solution set of some system, and it involves a free variable. So we could say that that solution set is in parametric vector form if it can be written in the form some vector x is a free variable, or a parameter t, times a vector v. So that's very similar to what we saw in this first example, our solution set X was equal to some vector V times our parameter T. Or if we could write this in the form, X as a vector is a linear combination of two vectors U and V with weights given by S and T, where S and T are any real numbers, so free variables or parameters we might call them. So we saw that sort of solution set in this last example. X was a linear combination of these two vectors A and B, where S and T were taken to be any real numbers or free variables. So these sorts of equations are what are called parametric vector equations for a solution set. So let's look at some other examples now that we have this terminology, very similar to what we've been working with, just using our new terminology. So in this next problem, we are asked to solve the homogeneous linear system given here, and then write our solution set in parametric vector form. So just like our previous examples, let's start by considering the augmented matrix for this system. Here we have 1, 3, -5, 0, 1, 4, -8, 0, and -3, -7, 9, 0. So using row reduction, well, in our first row, we have a lead coefficient of 1, and we need to eliminate the 1 and -3 below it. To eliminate the 1 as the lead coefficient in my second row, I'll take row 2 minus row 1. So my first row remains 1, 3, -5, 0. My second row gives me, let's see, 1 minus 1 is 0, 4 minus 3 is 1, -8 minus the -5, or plus 5, is -3, and 0 minus 0 is 0. Now to eliminate the -3 for the lead coefficient in my third row, I'll take row 3 plus 3 times, I could use 3 times row 1 or 3 times row 2. I'm going to stick with row 1 here, so I would have 3 minus 3 is 0, 9 minus 7 is 2, -15 plus 9 gives me a 6, or -6, and then my 0 plus 0 is 0. So we can see here again pretty quickly that our second and third rows are scalar multiples of one another. That is, they're defining the same equation. In order to, so we see that we will have a free variable here, at least one. So let's look at simplifying a little further. So to move further towards a reduced row echelon form, I might take row 3 minus twice row 2. So that would give me my second row as 0, 1, -3, 0. And when I perform this operation on my third row, I have 0, 0, 0, 0. Now in this same step, I want to try to eliminate the +3 that appears above the 1 in that lead coefficient for my second row. So let me take row 1 and subtract 3 times row 2, which would leave me 1, 0. Let's see, 9 minus 5 would be 4, and 0. So now this is in reduced row echelon form, and we see that our third column does not have a pivot position. So there will be a free variable for our third variable, x3 here. So let x3 be a free variable, and let's choose some value for x3. We'll denote our choice of real number by t. And this is a free variable. So to solve for x1 and x2, we can use the first or second row of this augmented matrix. And our first row tells us that 1x1 plus 4 times x3, which was t, equals 0. So x1 is negative 4t. And using the second row of our augmented matrix, we have 1x2 minus 3 times x3, or 3 times t, is equal to 0. So x2 is equal to 3t. All right. So our solution set, written in parametric vector form, would be the set of vectors x of the form x1 is negative 4t, x2 is 3t, and x3 is t. Or in parametric vector form, we have to factor out that t, and we're left with the vector negative 4, 3, 1 times t, where t can be any real number. All right. So again, geometrically, this solution set represents a line passing through the origin and in the direction of this vector, negative 4, 3, 1. So if we wanted to try visualizing this, let's do a little scratch work to the side here. So our coordinate system in space, we have the positive x-axis, y-axis, and z-axis. And this vector, let's give it a name. I'm going to call our direction vector v here, is moving in the direction, let's see, I've got my axes reversed here. I want this to be x, y, and z, so that we're following the right-hand rule for the orientation. So for x, we had an x component of our vector of negative 4. So we're going to be moving in the negative x direction 4 units. And our y component was positive 3. So in the positive y direction, we're moving 3 units. And then in the z direction, we've got a positive 1. We're moving upward 1 unit. So our point, we move from the origin, 0, 0, 0, to the terminal point given by this point negative 4, 3, 1 in space. And what we're doing is we're taking that vector v and we're looking at all scalar multiples of it. We're multiplying by all real values of t. So by scaling the length of that vector, well, we're looking at all vectors in the same direction of shorter length or larger length. Or if we take negative values for t, we reverse the direction of our vector v. And then by looking at all scalar multiples of it, we're defining this line, which we could maybe denote as L, through space. So every point on that line is a solution of this system. All right. So let's look at some other examples that are similar. Here, we are asked to describe all solutions of the homogeneous system written in matrix equation form as A times X equals 0, where A is row equivalent to the given matrix. So here, A is row equivalent to the matrix that we're given. So we want to describe our solution set, we're told, in parametric vector form. So looking at part A here, we have a coefficient matrix, which is 2 by 4. So 2 equations in the variables x1, x2, x3, and x4. And we see that it's already in echelon form, but not reduced echelon form. So we have a 1 as our lead coefficient with the 0 below it. And in our second row, we have a lead coefficient of 1, but we need to eliminate the -2 above it. So to put this in reduced echelon form, we could simplify a little bit by taking my first row and adding 2 times the second row to it. So my second row remains the same. 0, 1, 2, -6. And our first row, when we perform this operation, becomes 1, let's see, 2 minus 2 is 0, 4 plus our -9 is -5, and then minus 12 plus 5 gives us a -7. Now we're looking at solutions of a homogeneous system. So since our right-hand side of this equation is the 0 vector, we could think about this as an augmented matrix here, where we set this equal to the 0 vector. All right. So now the coefficient matrix A that we were given is now in reduced row echelon form, and we see that it has 2 pivot positions, and the third and fourth columns corresponding to the variable x3 and x4 do not have pivot positions. So we're going to let those 2 variables be free variables. So let's make our choice for x3 and x4. Here I'm going to let x3 be t, and x4 equal s, be free variables. So to solve for x1 and x2, we use our first 2 equations, our first 2 rows of our matrix. So the first row of this matrix says 1x1 minus 5 times x3, which I chose as t, minus 7 times x4, which I chose as s, has to equal 0. So x1 is equal to 5t plus 7s. And our second equation, our second row in equation form, says 1x2 plus 2 times x3, which was t, minus 6 times x4, which we let be s, is 0, or x2 is -2t plus 6s. So our solution set here would be the set of vectors where x1 is given by 5t plus 7s, x2 is -2t plus 6s, x3 is t, and x4 is s. Or writing this in parametric vector form, pulling out the coefficients for t, we have 5, -2, 1, 0 times t, plus 7, 6, 0, 1 times s, where t and s can be any real numbers. All right. So here, our solution set would be sort of a plane, but in 4-dimensional space, R4, since we've got 4 variables, which are spanned by the vectors given here. All right. So let's look at another one. In part B, we've got the same sort of problems, but a larger dimensional system here. So here we have a 4 by 6 matrix. So 4 equations in 6 variables, x1, x2, x3, x4, x5, and x6. And we see here that it is in echelon form. So we have this sort of stair-step pattern, but it is not in reduced echelon form. So in particular, for my leading one, I've got zeros below this and above it. For the leading one in my second row, I have zeros below it, but I need to eliminate the -2 that appears above it. So let's do that in our first step here. I'm going to take row 1 plus twice row 2. So let's see what this gives me. I have, for my first row, 1, -4. My 2 minus 2 becomes a 0, 0, 3, and -2 plus my -5 is -7. My second row is 0, 0, 1, 0, 0, -1. My third row is 0, 0, 0, 0, 1, -4. And my last row was a row of all zeros. All right. So now my lead coefficient in the first row is 1. I have zeros above and below it. The leading coefficient in my second row is 1. I've got zeros above and below it. And my leading coefficient in my third row is a 1 with zeros below it, but I still have to kill off this factor of 3 in the first row. So to do that, we can take row 1 and subtract 3 times row 3. So let's see what this gives us. We have 1, -4, 0, 0. Then my -3 plus 3 becomes a 0. And then I'll have a +12 minus 7 leaves me with a +5. My second row is 0, 0, 1, 0, 0, -1. Third row is 0, 0, 0, 0, 1, -4. And my last row consisted of all zeros. So we have our matrix in reduced row echelon form, where we have 3 pivot positions, but recall that there were 6 variables. So here we do not have a pivot position in our second column, which corresponds to the variable x2, in our fourth column, which corresponds to x4, or the sixth column, which corresponds to x6. So those variables will be chosen as free variables. So let's make a choice for these values. So let's say let x2 be, let's see, I've been using s and t so far. So let's maybe just stick with these x values. So let x2, x4, and x6 be free variables. I won't use a different variable to denote my choice for these values. So solving for the remaining variables, well, our first equation gives us x1 minus 4 times x2 plus 5, x6 has to be 0. Recall we have 0 on our right-hand side since we were considering homogeneous systems, something of the form ax equals 0. For our second row, we have the equation x3 minus x6 has to equal 0. And for our third row, we have the equation x5 minus 4 times x6 is 0. So solving for x1, we have 4x2 minus 5x6. Solving for x3, we have x6. And solving for x5, we have 4 times x6. So let's see if I can write this in the parametric vector form we were asked for. I'll have to run onto the next page here. So we had x was a set of 6 values, or 6 variables, x1 through x6. x1 was given by 4x2 minus 5x6. x2 was free. x3 was equal to x6. x4 was a free variable. x5 was equal to 4 times x6, and x6 was a free variable. So if we split this in parametric vector form, let's start by pulling out the values for x2. So we had 4x2, 1x2, and then no x2s in my remaining equations. Plus, for x4, the next free variable, the only place x4 appeared was for the variable x4 itself. So we have 0, 0, 0, 1, 0, 0 times x4. Plus, for x6, we had coefficients of -5, 0, 1, 0, 4, 1 times x6, where x2, x4, and x6 can be chosen as any real number. So here we have a solution set which is spanned by the 3 vectors shown here. All right. So let's look at some other examples. Moving on to our next one here, we have the following problem. Let us suppose that the solution set of a system can be described as x1 is equal to 3x4, x2 is 8 plus x4, x3 is 2 minus 5 times x4, with x4 being free. So we're told to use vectors to describe this set as a sort of line, but in 4-dimensional space. All right, so let's write out our solution in parametric vector form. So starting with vector form, we had 4 variables where x1 was equal to 3 times x4, x2 was 8 plus x4, x3 is 2 minus 5 times x4, where x4 was a free variable. So if we were to pull out the coefficients for x4, we have 3 times x4. And let's see, I need to be a little bit careful here. We don't have just these free variable terms, but here we also have constant terms such as 8 or 2, add with where we're adding or subtracting some scalar multiple of x4. So let me start by pulling out the constant terms from each variable. So the constant terms from each of x1 through x4 would be 0, 8, 2, and 0. And then we are adding to that the following. We have the coefficients of x4, which were 3, 1, -5, and 1, all times x4. Or if we prefer, if we were to let or choose a specific value for our free variable, say some real number t, then our solution set would be the set of vectors x, which have the form 0, 8, 2, 0. And then we are adding the scalar multiple of the vector 3, 1, -5, 1, where we're scaling by this vector t. So this would be our solution set, and we're told to describe this set as a sort of line in R4. So here we have a sort of line. We're using quotations around line since it's not in R2 or R3, but we have a line in 4-dimensional space, R4, which passes through the point 0, 8, 2, 0, because if we chose t equal to 0, we would have x is equal to this point. So we have a line which is passing through this point and is moving in the direction of the vector 3, 1, negative 5, 1. That is the vector that we are adding a scalar multiple of to get our solution. All right. So in the last part of this section, we'll consider some non-homogeneous systems. In fact, the last example that we looked at might be the solution set of a non-homogeneous system, and see how the solution set might be related to the solution set of a corresponding homogeneous system. So here, we are told to solve the non-homogeneous system. Now, why is this one non-homogeneous? Well, because the constants on the right-hand side of our equation are not all 0. So here we have a non-homogeneous linear system. We're told to solve this and then express our solution in parametric vector form and describe that solution set geometrically. So let's see what we have here. In order to solve our system, we will write this as an augmented matrix, 1, 3, negative 5, 4, 1, 4, negative 8, 7, and negative 3, negative 7, 9, negative 6. All right. So to simplify this, using row reduction, I might first take row 2 minus row 1. So my first row is 1, 3, negative 5, 4. My second row, if I subtract the first row, is 0, 1, negative 3, 3. And in order to get rid of the negative 3 as the lead coefficient in my third row, I will take row 3 plus 3 times row 1. So this gives me 0, 9 minus 7 is 2, negative 15 plus 9 is negative 6, and we've got a 12 minus 6 is 6. All right. So simplifying a bit further, I can take row 3 minus twice row 2. So this gives me a second row of 0, 1, negative 3, 3. When I perform this operation on my third row, I have 0, 0, 0, 0. Get a row of all 0, so we will have a free variable. And in this same step, I might also use this pivot of 1 to kill off the 3 in the first row. So if I take row 1 minus 3 times row 2, let's see what we have. I would have a 1, minus 3 plus 3 is 0, 9 minus 5 is 4, and negative 9 plus 4 would be a negative 5. So here we have our augmented matrix in reduced row echelon form, and we see that our third column does not have a pivot position, so we will let x3 be a free variable. And let's denote our choice for x3 maybe as t. So here, x3 equals t will be a free variable. And using our first equation, we see that 1x1 plus 4 times x3, or 4t, has to equal negative 5. So x1 is equal to negative 5 minus 4t. And x2, using the second equation, x2 minus 3t has to equal 3. So x2 is equal to 3 plus 3t. So our solution set for this system would be the set of vectors x, where x1 is equal to negative 5 minus 4t, x2 was 3 plus 3t, and x3 was the free variable t. So if I split this vector into the sum of two pieces, as we did with our previous example, well, let me start by pulling out the constant terms, my negative 5, 3, and 0 from each component of this vector. And then I will add the vector times the vector of coefficients of t times t itself. So here my coefficients were negative 4, 3, and 1 times t. So I've got negative 4, 3, 1 times t. So this is our solution set in parametric vector form. And then we're told to describe this solution set geometrically. So as we saw with that previous example, here we would have a line through the point in space negative 5, 3, 0, and in the direction of this vector negative 4, 3, 1. All right. So one thing to notice here, one thing that I want to point out with this example is how this relates to one of our earlier problems. So let us recall this set of linear equations, in particular the equations on the left-hand, or the equation on the left-hand side of each side of my system. And let's recall where we've seen that same system before. Notice that the example that we did earlier was the exact same system that we had in that previous example. So we had the same coefficient matrix of 1, negative 3, 1, 3, negative 5, 1, 4, negative 8, and negative 3, negative 7, 9. And we saw that for this homogeneous linear system, where we had all zeros on the right-hand side, our solution set was a line in the direction of this vector, negative 4, 3, 1, passing through the origin. Now, if we look at that same set of equations, but we change the right-hand side of our equations to be 4, 7, and negative 6, well, let's see how that changed our solution. Here, our solution was a line which has the same direction as the line that we saw in our earlier example for the homogeneous system. It moved in the direction of negative 4, 3, 1. But instead of passing through the origin now, we have a point or a line which is passing through this point, negative 5, 3, 0. So we have a line which is parallel to the line describing the solution of the homogeneous system, but passing through a different point. And the point that we're passing through is determined by what constants we have on this right-hand side of our equation. So what this last example is illustrating is if we have a non-homogeneous system, which has infinitely many solutions, then the general solution of that system can be written in parametric vector form as one vector. So maybe this vector negative 5, 3, 0, plus an arbitrary linear combination of vectors that satisfy the corresponding homogeneous system. So I'm taking some arbitrary scalar multiple of a solution of my homogeneous system. Okay? So there is a relationship between the solution sets for homogeneous systems and non-homogeneous systems that have the same coefficient matrix. So to make this a little more precise, let's look at the following theorem. So let's suppose that we have a linear system, which can be described by the matrix equation AX equals B. And this system is consistent for some given vector B, so a solution exists. And let's call P a solution of that system. So if we consider the solution set of AX equals B, that is the set of all possible solutions, we would be looking at the set of vectors of the form X, which are equal to P, that is the solution, one particular solution of this linear system, plus some vector V sub H, where V sub H is any solution of the corresponding homogeneous system AX equals the 0 vector. So if we find one solution of a linear system, and I know the solution of the homogeneous, corresponding homogeneous system, I can construct every solution of that system by taking the sum of those values. So let's look at our last example here, where we are told to describe and compare the solution sets of the following two equations. So in our first equation, we have the single linear equation x1 minus 3x2 plus 5 times x3 is equal to 0. So it is a single equation involving three variables. So one way to describe this would be by solving for x1 in terms of x2 and x3. So x1 would be 3x2 minus 5x3, which would describe all possible solutions. So if we were to introduce free variables here for x2 and x3, we would have a plane in space which satisfies these equations. So we have the set of points x1, x2, x3, where x1 is equal to 3x2 minus 5x3, and x2 and x3 can be any real numbers. Or if we wanted to write this maybe in parametric vector form, we would have the set of vectors where x1 was 3x2 minus 5x3, x2, x3. Or, splitting this up, I would have 3, 1, 0 times x2 plus negative 5, 0, 1 times x3. All right, so our solution set would be a plane in space spanned by these two vectors. Now, if we're comparing the solution set of this equation to the solution set of the corresponding non-homogeneous equation, where we set that same equation equal to 4, let's see how these compare. So if we had the equation x1 minus 3x2 plus 5x3 is 4, or if we were to solve for x1 in terms of the other variables, we have 3x2 minus 5x3 plus 4. So writing our solution set in parametric vector form, we have the vector where x1 is 3x2 minus 5x3 plus 4, and x2 and x3 were free variables. So splitting this up, we would have a vector of constants where the only constant was in our first coefficient. We have 4, and then we had 0 and 0 for the constants in our second and third components. So we would have 4, 0, 0, plus, if we factor out the x2 coefficients, we have 3, 1, 0 times x2, plus, when we factor out our x3 coefficients, we have negative 5, 0, 1 times x3. So notice that this solution set of the homogeneous equation appears exactly here. So we have a plane which is spanned by these two vectors, 3, 1, 0 and negative 5, 0, 1. But for the non-homogeneous equation, we've just shifted that plane by a factor of 4 in the x1 direction. So here our solution sets describe parallel planes in space. So here the solution sets are parallel planes in space. All right, so just like we saw in our earlier example, the solution set of a homogeneous equation was a line through the origin. If we made it a non-homogeneous equation, it was a line which is parallel to that line, but no longer through the origin. Here, for this example, we have a homogeneous solution set, which is a plane through the origin spanned by two vectors. And if we look at the corresponding non-homogeneous equation, we have a plane spanned by the same two vectors, but not passing through the origin. It's been shifted by 4 units in the x1 direction. All right. So that finishes our section 1.5 material on solution sets of linear systems. So in this section, we haven't really introduced too many new techniques. We're still solving systems the same way, but we're starting to see a new way to express solution sets if we have free variables using what's called parametric vector form. And we saw that there is a relationship between the solution set of a homogeneous linear system and a non-homogeneous system that has the same coefficient.